Welcome back to the Nocturnal Astronomer. I'm your host, Atlas Reed. Tonight, I want to tell you something remarkable before we begin. Somewhere out there, two black holes once spiraled together in perfect silence, and the universe itself rang like a bell. That ringing crossed more than 1 billion years of space and finally reached us right here on Earth as the faintest tremor in the fabric of reality. This evening, we drift into the story of gravitational waves, the silent symphony written into the geometry of space-time itself. We will trace this idea from a quiet doubt in Einstein's mind to the vast machines built to listen for whispers smaller than a proton. Let your body settle, let your thoughts slow, and let the cosmos hum you gently towards sleep. Let's dive in. Part 1. Einstein's prediction of ripples in spacetime. In 1915, Albert Einstein completed his general theory of relativity, a quiet revolution in how we understand gravity. Instead of an invisible pull between masses, he described gravity as the curving of space-time itself. A star, a planet, a moon, each one presses a gentle dent into the fabric around it, and other bodies follow the curves of that dent. The following year, in 1916, Einstein extended his theory further. If mass can curve space-time, he reasoned, then a moving mass should send ripples outward through that same fabric, much like a stone dropped into still water. He called these ripples gravitational waves, faint disturbances traveling outward at the speed of light itself, carrying no matter, only pure geometry. Yet Einstein himself doubted these ripples would ever be heard. He calculated that even the most dramatic cosmic events would produce waves so faint that no instrument built by human hands could ever hope to sense them. For decades, gravitational waves remained a beautiful idea on paper, a prediction resting quietly inside the mathematics of general relativity, waiting patiently for technology to catch up. To understand what a gravitational wave truly does, picture space itself as something soft and elastic. As a wave passes through a region, it stretches space gently in one direction while squeezing it in the direction perpendicular. The effect is unbelievably small, changing distances by a fraction smaller than the width of a single atom, yet it happens across enormous stretches of the cosmos. Scientists often describe gravitational waves as a kind of cosmic sound, though nothing about them is audible in the way we normally think of sound. Instead, when detectors capture a gravitational wave, researchers can translate its pattern into an audible chirp, a rising tone that mirrors the rhythm of two bodies spiraling closer together, moving faster and faster before their final union. Only the most massive and swiftly moving bodies in the universe produce gravitational waves strong enough to notice. Two black holes circling one another, two neutron stars drawing together, or the sudden collapse of a dying star can all send ripples strong enough to cross unimaginable distances. Even the birth of the universe itself may have stamped a faint gravitational signature onto the fabric of space-time. For nearly a century, this prediction sat untested, a graceful equation with no proof beside it. Physicists wondered whether these ripples were real in any measurable sense, or simply an elegant mathematical shadow. The answer would not come quickly. It would take patient observers, clever instruments, and one particularly stubborn pair of neutron stars to finally offer the first hint that Einstein had been right. Part 2. The Long Wait for a Whisper. By the 1970s, astronomers had no direct way to detect gravitational waves, but they began searching for indirect clues instead. If two massive bodies orbited one another and slowly lost energy to gravitational waves, that energy loss should show up as a gradual shrinking of their orbit. All that was needed was a system precise enough and patient enough to reveal such a subtle change. In 1974, astronomers Russell Hulse and Joseph Taylor found exactly such a system while using a large radio telescope in Puerto Rico. They discovered a pulsar, a rapidly spinning neutron star that sweeps a beam of radio waves past Earth with astonishing regularity, orbiting closely around another neutron star. Together, this pair became known as a binary pulsar, ticking with remarkable precision. A pulsar behaves like a natural clock in the sky, spinning and flashing with a rhythm so steady that astronomers can measure tiny shifts in its timing. By tracking the arrival of each pulse from this distant binary system, Hulse and Taylor could calculate the orbit of the two neutron stars with extraordinary accuracy, watching how their paths changed ever so slightly across the years. Over years of careful observation, the two neutron stars were found to be spiraling closer together, their orbital period shrinking at a rate that matched Einstein's equations almost perfectly. The only explanation was that the system was losing energy by radiating gravitational waves outward into space, exactly as general relativity had predicted decades earlier. It was indirect proof, but powerful proof nonetheless. This careful, patient body of work earned Hulse and Taylor the Nobel Prize in Physics in 1993. Their discovery gave physicists their first real confidence that gravitational waves were not merely a mathematical curiosity, but a genuine feature of the universe, quietly draining energy from orbiting bodies across the galaxy, even if no instrument had yet caught the waves themselves in the act. Still, hearing about gravitational waves secondhand, through their gentle effect on a distant orbit, was not the same as detecting them directly. physicists dreamed of building an instrument sensitive enough to feel spacetime itself stretch and squeeze as a wave passed through our own planet. Such a machine would need to notice a change smaller than a fraction of the width of a proton. That dream would take another 2 decades of careful engineering to become real. Scientists across the world began designing instruments delicate enough to catch a gravitational wave in the act, rather than simply inferring its presence from a shrinking orbit far away. What they eventually built would become one of the most sensitive machines ever constructed by human hands. Part 3. Building an instrument to hear the universe. The instrument that finally succeeded is called LIGO, short for the Laser Interferometer Gravitational Wave Observatory. It consists of 2 nearly identical facilities within the United States, one resting in Hanford, Washington, and the other in Livingston, Louisiana. Placing these stations so far apart from one another allows scientists to confirm that any signal detected came from the cosmos rather than from a local disturbance nearby. Each LIGO facility is shaped like an enormous letter L, with 2 arms stretching 4 kilometers in perpendicular directions across the landscape. Inside each arm, a carefully tuned laser beam travels down a vacuum tube toward a mirror, then bounces back toward its starting point. Under normal conditions, the light returning from each arm cancels out in a precise and predictable way. When a gravitational wave passes through the observatory, it very slightly stretches one arm while squeezing the other, changing their lengths by an almost impossibly tiny amount. This shift disturbs the careful cancellation of the returning laser light, producing a faint but measurable flicker. From that flicker, scientists can calculate the size and rhythm of the wave that just swept through the instrument. The precision required for this task is difficult to imagine. LIGO can detect a change in arm length 10,000 times smaller than the width of a single proton, one of the tiniest particles known to physics. To achieve this, engineers had to guard against nearly everything: distant traffic, seismic tremors, temperature shifts, and even the quiet vibration of the mirrors themselves at room temperature. After its initial construction, LIGO underwent a major upgrade known as Advanced LIGO, completed in 2015. This upgrade multiplied the sensitivity of the original design many times over, finally bringing the instrument close enough to theoretical limits that a real gravitational wave passing through Earth might actually be noticed. Physicists switched the upgraded detectors on that same year, uncertain what, if anything, they might hear. The vision behind LIGO took shape over decades, driven largely by physicists Rainer Weiss, Kip Thorne, and Ronald Drever, who each contributed crucial ideas to its design. Weiss first sketched the basic concept of a laser-based detector in the 1970s, while Thorne helped calculate what kind of cosmic events might produce a signal strong enough to notice. Their patient collaboration spanned much of their careers. By September of 2015, the newly upgraded detectors sat quietly in Washington and Louisiana, running their engineering tests before the official observing period had even begun. Nobody expected a detection so soon, and yet, in the early hours of the 14th, something reached both facilities within a fraction of a second of one another, a signal unlike anything ever measured before. Part 4. The First Whisper Ever Heard. In the pre-dawn hours of September 14th, 2015, a signal swept through both LIGO detectors within 7/1000ths of a second of each other. It lasted barely a fifth of a second from start to finish, yet within that brief flicker, it carried the story of two enormous bodies spiraling together in the final moments before their union, far across the universe. When researchers converted the signal into sound, it produced a distinctive chirp, a tone that rose steadily in both pitch and loudness before ending abruptly. This chirp is the signature of two bodies orbiting one another ever faster as they draw closer, until they finally merge into one. The pattern matched almost perfectly with predictions calculated decades earlier from Einstein's equations. After careful analysis, scientists identified the source as two black holes, each many times more massive than our Sun, spiraling together and merging into a single larger black hole. The event had unfolded roughly 1.3 billion years earlier, its ripples travelling outward at the speed of light ever since, only now reaching Earth and brushing gently against LIGO's waiting mirrors. During the final instant of their merger, the two black holes released more power as gravitational waves than the combined light of every star in the observable universe, if only for the briefest fraction of a second. None of that energy arrived as light. It travelled instead as a pure ripple in the shape of space-time, silent to the ear but thunderous in its geometry. Scientists spent months double-checking the signal, ruling out any possibility of error, before finally announcing the detection to the world in February of 2016. The announcement confirmed, for the first time in history, a direct observation of gravitational waves, a full century after Einstein first proposed their existence within his theory of general relativity. The achievement earned the Nobel Prize in Physics in 2017, awarded to Rainer Weiss, Barry Barish, and Kip Thorne for their decisive contributions to LIGO and the detection of gravitational waves. Their work represented not the effort of three individuals alone, but the culmination of a collaboration involving more than 1,000 scientists across the globe, working together over many years. That first whisper, so faint it barely nudged the mirrors of two instruments on opposite sides of a continent, opened an entirely new way of listening to the universe. For the first time, humanity could sense the universe not only through light, but through the gentle trembling of space itself. And this was only the beginning of what those trembles would reveal. Part 5. Two black holes meet in the dark. To appreciate what LIGO actually detected, it helps to picture the two black holes themselves. Each was invisible by nature, a region where gravity grows so strong that nothing, not even light, can escape its pull. One held roughly 36 times the mass of our Sun, the other about 29 times, both squeezed into a space smaller than a modest city. For ages beforehand, these two black holes likely circled one another at a comfortable distance, slowly drawing closer as they lost energy to gravitational waves. In the final moments before their union, that slow drift became a plunge. Their orbital speed climbed until they were circling each other hundreds of times per second, reaching a notable fraction of the speed of light itself. When the two finally met, they merged into a single, larger black hole, holding about 62 times the mass of our Sun. Simple arithmetic suggests the result should have held 65 solar masses, the sum of the two originals. The missing 3 solar masses had not vanished. They had been converted directly into the energy of gravitational waves, radiated outward across the cosmos. After the merger, the newly formed black hole briefly rang like a struck bell, wobbling through a phase astronomers call the ring down before settling into a calm, stable shape. This ringing carried its own gravitational signature, distinct from the earlier chirp, offering scientists a way to test whether the final black hole matched the smooth, simple shape predicted by Einstein's equations. The merger unfolded somewhere in the southern sky, at a distance so vast that its light, had there been any light at all, would have taken roughly 1.3 billion years to reach Earth. Because black hole mergers produce no visible light of their own, gravitational waves offered the only possible way for anyone on Earth to ever learn that this union had occurred. This single detection confirmed something astronomers had long suspected but never directly proven: that pairs of black holes can form, orbit one another, and eventually merge within the age of the universe. It also demonstrated that gravitational wave astronomy could reveal entire classes of cosmic happenings invisible to every telescope ever built, since black holes alone emit no light for any instrument to gather. With this single, silent chirp, an entirely new field of astronomy had proven itself real. Scientists now held a tool capable of sensing the darkest, most hidden bodies in the universe, bodies that no telescope could ever hope to photograph directly. The quiet trembling of space-time had become a genuine window onto some of the most mysterious happenings the cosmos has to offer. Part 6. A New Sense for Astronomy. For centuries, astronomy relied almost entirely on light, gathering it with ever larger telescopes to study distant stars and galaxies. Gravitational wave detection introduced something fundamentally different, closer to a sense of hearing than a sense of sight. Instead of gathering photons, LIGO senses the gentle stretching and squeezing of space itself, offering an entirely new channel of information about the universe. Astronomers now speak of multi-messenger astronomy, the practice of combining gravitational wave signals with traditional light-based observations, radio waves, gamma rays, and even particles called neutrinos. When several of these messengers arrive from the same cosmic event, they offer a far richer picture than any single method could provide alone, each one revealing details the others simply cannot capture. Light-based astronomy struggles to reveal certain kinds of events entirely. Black holes emit no light of their own, and some of the densest, most energetic happenings in the universe unfold behind thick clouds of gas and dust that block visible light almost completely. Gravitational waves pass through such barriers with ease, carrying their message from deep within these hidden and shrouded regions. Because gravitational waves arise directly from the motion of mass, they carry information that light simply cannot. From a single chirp, scientists can calculate the masses of the bodies involved, how quickly they were spinning, and the exact distance the signal traveled to reach Earth, all without ever needing to see a single photon emitted by the event itself. As confidence in this new sense grew, scientists expanded their listening network. Virgo, a detector built in Italy, joined LIGO in the effort, followed later by Kagra in Japan. With detectors spread across different continents, researchers could triangulate the direction a gravitational wave had come from far more precisely, narrowing its origin down to a small patch of sky worth further study. Since that first detection in 2015, the number of confirmed gravitational wave events has grown into the hundreds, cataloguing mergers between pairs of black holes, pairs of neutron stars, and even mismatched pairs combining one of each. Each new detection adds another piece to our understanding of how these dense, dark bodies form, pair up, and eventually meet across the universe. Yet, among all these detections, one stood apart from the rest, arriving not as a silent chirp alone, but accompanied by a burst of light visible across nearly every part of the electromagnetic spectrum. That happening, unfolding in the summer of 2017, would connect gravitational waves to something far more tangible. intangible, the very origin of gold and other precious elements scattered throughout the cosmos. Part 7. When neutron stars collided and made gold. On August 17th, 2017, LIGO and Virgo together captured a gravitational wave signal unlike any before it. Rather than the short, sharp chirp typical of colliding black holes, this signal stretched on for roughly 100 seconds, a much longer song produced by two far lighter bodies, neutron stars, spiraling together instead of a heavier pair of black holes. A neutron star forms when a massive star collapses at the end of its life, crushing an amount of matter greater than our Sun into a sphere only about 20 kilometers across. A single teaspoon of this material would weigh billions of kilograms here on Earth. When two such dense bodies spiral together, they produce gravitational waves quite unlike those from merging black holes. Roughly 2 seconds after the gravitational wave signal ended, space-based telescopes detected a brief burst of gamma rays arriving from nearly the same patch of sky. This near-simultaneous arrival confirmed something remarkable, that the merger of two neutron stars produces both gravitational waves and a genuine burst of light, allowing astronomers to observe the very same happening through two entirely different channels at once. Word of the detection spread quickly among astronomers worldwide, and within hours, dozens of telescopes turned toward the indicated region of sky. They located a fading point of light within a galaxy roughly 130 million light-years away, marking the first time scientists had ever paired a gravitational wave detection with a visible counterpart glowing in ordinary light. This glowing afterglow, known as a kilonova, offered something astronomers had hoped to find for decades: direct evidence of where many heavy elements in the universe are forged. Within the debris flung outward by the collision, atoms of gold, platinum, and other precious metals formed through rapid nuclear reactions, seeding the surrounding galaxy with material that may one day join a new star or a planet. Before this happening, scientists debated exactly where the universe's heaviest elements came from, since ordinary stars can only forge material up to iron before running out of nuclear fuel. The neutron-star merger offered strong evidence that collisions like this one, however rare, may account for a substantial share of the gold, silver, and other precious metals found scattered throughout the universe today. Somewhere in the debris of that ancient collision, the very atoms that might rest in a wedding ring or a golden coin, or beneath the surface of a distant world, were forged in a moment of gravitational and electromagnetic brilliance far across the universe. It stands as one of the most beautiful reminders that we are, in a very real sense, made stardust. Part 8. Listening with many ears across the globe. As LIGO proved gravitational wave astronomy possible, other nations built their own detectors to join the effort. Virgo, located near Pisa in Italy, began contributing to the search in the summer of 2017, only weeks before the neutron star merger was detected. Its design closely resembles LIGO's, using long perpendicular arms and carefully tuned laser light to sense passing waves. Japan later added its own detector, named Kagra, built deep underground within a mountain to shield it from surface vibrations and placed at extremely cold temperatures to reduce thermal noise within its mirrors. Together with LIGO and Virgo, Kagra extended the growing global network, adding another set of ears listening for the faintest tremors passing through the fabric of spacetime. Having several detectors spread across different continents allows scientists to pinpoint where a gravitational wave signal came from far more precisely than any single instrument could manage alone. By comparing the tiny difference in arrival time between stations, researchers can triangulate a rough direction in the sky, then guide traditional telescopes toward that same patch to search for any visible counterpart. Additional detectors are now planned or under construction, including LIGO India, expected to join the global network in the years ahead, along with proposed future instruments in Europe called the Einstein Telescope, and in the United States called Cosmic Explorer. Each new addition promises greater sensitivity, capable of catching fainter signals from farther across the observable universe than ever before. With each new detector added to the network, the rate of confirmed detections has climbed steadily. What once felt like a single, extraordinary whisper heard in 2015 has grown into a regular chorus of chirps and hums, arriving from mergers across the cosmos on a nearly weekly basis whenever the detectors are actively observing the sky together. This achievement rests on a truly global collaboration, drawing together thousands of scientists, engineers, and technicians from dozens of countries, each contributing expertise toward a shared and patient goal. Few scientific projects demand such sustained cooperation across so many borders, cultures, and institutions, all working quietly toward the same aim of listening more clearly to the whispers of the universe. Yet, even this growing network of ground-based detectors can only hear a certain range of gravitational frequencies, much like a human ear can only hear certain pitches of sound. To sense far lower, slower ripples in spacetime, scientists turned toward an entirely different method, one that relies not on lasers and mirrors, but on the steady ticking of pulsars scattered across our galaxy. Part 9. The Hum Beneath the Universe. Beyond the frequencies that LIGO and Virgo can sense lies a much slower, deeper set of gravitational waves, ones that stretch and squeeze space over the course of years rather than fractions of a second. To detect ripples this slow, astronomers rely on an entirely different tool, a collection of pulsars scattered across the galaxy, each ticking with remarkable natural precision. By carefully timing the arrival of pulses from dozens of these natural clocks spread across many directions in the sky, astronomers can search for a very particular pattern, a faint, coordinated shift in timing that would appear if a gravitational wave were slowly passing through our entire galaxy, gently stretching and squeezing the space between Earth and each distant pulsar. In 2023, several international teams announced strong evidence of exactly this kind of signal after studying pulsar timing data gathered over 15 years. Rather than a single, sharp chirp, this discovery revealed something more like a low, constant hum spread across the entire sky, a background presence rather than one isolated happening. Scientists believe this steady hum arises from countless pairs of supermassive black holes, each holding the mass of millions or even billions of suns, slowly orbiting one another at the centers of merging galaxies throughout the universe. With so many such pairs scattered across the cosmos, their overlapping gravitational waves blend together into a continuous, low-frequency background rather than distinct chirps. This background hum offers valuable insight into how galaxies grow and merge over cosmic history. Nearly every large galaxy, including our own, is thought to hold a supermassive black hole at its center. When two such galaxies merge, their central black holes eventually spiral together as well, adding one more faint voice to the vast, low-frequency chorus filling the universe. Detecting this hum required an extraordinary feat of patience and precision, since the timing shifts involved amount to mere nanoseconds spread across many years of careful observation. Pulsars had to be monitored again and again with large radio telescopes, their arrival times compared with painstaking care before any confident pattern could emerge from what might otherwise look like ordinary noise. Together, the sharp chirps caught by LIGO and Virgo and the slow, steady hum revealed by pulsar timing arrays paint a picture of a universe filled with gravitational sound at every scale, from the briefest cosmic instant to rhythms unfolding across many years, and still an entire range of frequencies in between remains largely unheard, waiting for the next generation of instruments to arrive. Part 10. Listening from Space and What Comes Next. To fill that missing range of frequencies, scientists are now building a detector unlike any that came before it, one that will operate not on Earth, but in space itself. Known as LISA, or the Laser Interferometer Space Antenna. This mission is being developed by the European Space Agency, with plans to launch sometime in the 2030s. LISA will consist of 3 spacecraft arranged in a vast triangle and connected by laser beams stretching across millions of kilometers of empty space between them. Free from the seismic tremors and gentle vibrations that limit detectors on Earth, this spacecraft trio will be able to sense far slower, gentler ripples in space-time than any ground-based instrument could ever hope to notice. Once operating, LISA should be able to sense the gravitational waves produced when supermassive black holes merge during galaxy collisions, along with signals from smaller, closer pairs of white dwarfs orbiting one another within our own galaxy. These sources produce waves at frequencies far too low for LIGO or Virgo to notice, but perfectly suited to LISA's much longer arms. Some physicists hold an even more ambitious hope that future detectors, whether in space or on Earth, might eventually catch a much fainter signal, the gravitational waves theorized to have rippled outward during the very first moments after the Big Bang itself. Such a signal would offer a direct glimpse into conditions from the earliest instant of the universe's existence. In barely a decade since that first detection in 2015, gravitational wave astronomy has grown from a single, hard-won signal into an entire branch of science, complete with a global network of detectors, hundreds of confirmed happenings, and ambitious plans reaching decades into the future. Few fields in the history of astronomy have advanced so quickly from theory into routine observation. It is worth remembering that Einstein himself doubted these waves would ever be detected, considering them far too faint for any instrument built by human hands. A century later, patient engineering, careful mathematics, and a great deal of international cooperation proved him wrong in the gentlest possible way by finally catching the faintest whisper his own equations had quietly promised all along. As you drift tonight, consider that the space around you, the very air resting between these words and your ears, has likely been touched by a gravitational wave at some point, stretched and squeezed by amounts too small to ever notice. The universe hums constantly around us, a silent symphony playing on, whether or not anyone is listening closely enough to hear it. And on that note, we come to the end of tonight's journey through the silent symphony of gravitational waves. From Einstein's quiet doubt to the whispered chirp of 2 black holes merging across 1 billion years of distance, we have traced how patient minds turned an elegant equation into genuine sound. Somewhere out there, space-time is still trembling gently, carrying stories older than our sun. We followed that trembling From a shrinking pulsar orbit in the 1970s to the first confirmed detection in 2015, and onward to a merger of neutron stars that scattered gold across the universe. We listened to a slow hum drifting between supermassive black holes, and we looked ahead toward instruments waiting patiently in space, ready to catch whispers still too faint to hear. Thank you for spending this quiet time with me tonight, drifting through the trembling fabric of space-time together. I hope these gentle ripples carried you toward rest, the way they have carried their stories across billions of years to reach us. I'll see you next time.